Okay, now the next thing I want to look at is a subject called related rates. And to introduce that, let me just remind you what you learned about differentiating with implicitly defined relationships. So, for example, well, let's think about this. We said that if you have x squared plus y squared equals 1, we said, well, I want you to find dy dx. Well, what we're saying is we're saying y is a function of x. X is the independent variable, y is the dependent variable. So what we do is when we differentiate, we go through and we differentiate x just like always. It's just the independent variable, the derivative of x is 1. So we just say 2x. Then when we come to the y, we say 2y, but we remember that y is a function of x, and we have to use the chain rule. So we always tack on a y prime, and then we solve for y prime. That's what we did with implicit differentiation. So, the principle is, let's suppose y equals 3x plus 2, something like that. Now, you know here that y prime is equal to 3. But let's suppose that, maybe I didn't know that. Let's suppose that I've got y to the 5th. Well, that's going to equal 3x plus 2 to the 5th. Now, if I differentiate, like we did there implicitly, notice what I would do. I would have 5y to the 4th times y prime. Well, let's see how that looks over there when we know what y is. It's going to be this. It's going to be 3x plus 2 to the 4th. Okay? Now look, that's y, right? Y is 3x plus 2 times y prime, which is 3. So look, we have the same thing. We have 5 times y to the 4th. 5y to the 4th times 3, y prime. So this was implicit differentiation. I mean, this was the kind of idea. We didn't know what y was strictly, implicitly, explicitly in terms of x, so we just went through this process. Now, let's suppose that we not only we know that y is a function of, let's say, t, some other variable, and let's suppose x is also a function of that third variable. In other words, maybe x and y are both a function of time. Well, our implicit differentiation takes a little bit of a new character. We've got x squared plus y squared equals 1. Now, we know that x and y are both functions of t, let's say. Well, now, that being the case, we have to apply the chain rule to both. We have 2x, x prime, where x is some function of t, plus 2y, y prime, equals 0. Because now x and y both, x is not just a function of, y is not a function of x, it's a function of t, x is a function of t. So we now have this x prime, which is dx dt, and y prime is dy dt. Okay? So they're functions of this parameter. Now, let me show you an example of with this example, this will kind of give you an overview of how we approach related rates problems. Let's suppose that you have this situation and we'll do a very simple one. Let's suppose that two people start here at A, and one person walks, let's say, east at 3 miles an hour. Okay, 3 miles an hour. And one person walks north at 4 miles an hour, let's suppose. Okay. Now, I'm going to look at the person that walks east. Let's say that their distance is a function of time. So if you start here at A and go out here, it's a function of time, right? So in 1 hour, you've walked 3 miles. In 2 hours, you walked 6 miles, and so forth. So I'm going to assign this distance right here. I'm going to assign that distance x, and it's a function of time. Okay? And I'll assign this distance up here. I'll assign this distance y, and it's also a function of time. Well, If we have that set up, what we can do is we can start thinking about, well, this hypotenuse here. So think about this. So this one person, we'll call him Jim, okay? Jim is walking east at 3 miles an hour, and Ted is walking north at 4 miles an hour. So look, here's what we have. We have dx dt is equal to 3, right? And we have that dy dt is equal to 4. So we have two rates there. Now, let's suppose we want to know how fast is the distance between the two changing. In other words, we want to know they're getting further apart from each other. We want to know how fast is that distance changing. In other words, with this picture, you can see it would be the hypotenuse right there. I'll just call that z. So here's what we want to find. We want to find dz dt. And let's do this. Let's find it after 1 hour. So let's find it for t equals 1, just for simplicity's sake. So we want to know, after they've been walking an hour, how fast is the distance between them changing? So here's the way we play the game. We say, okay, I've been given two rates of change, and before I know how those two rates of change are related, so that I can get the third rate of change, I'd like to know how x and y and z are related. In other words, there are three things here. There's x, y, and z. The change in x, the change in y, and the change in z. I would like to know, well, in general, how are those things related? How are those distances related? Well, you probably are thinking right now, Pythagorean theorem. I know that x squared plus y squared is equal to z squared. I know that. Well, if I know how those are related, then I can figure out how their derivatives are related, because I can just go through and differentiate. So I'll go through and I'll say, okay, 2x, x prime, and we'll understand when I say prime, I'm talking about the derivative with respect to t. So the derivative of x with respect to t, plus 2y, y prime, equals 2z, z prime. Okay? Now, I don't just have how the distances are related, I have how the rates of change are related. And let me go ahead, since I've got a 2 in all of these, let me just go ahead and divide out the 2. Okay? Now, what I'm wanting to know is how fast their distance between the two are changing after 1 hour, after they've been walking 1 hour. Well, I can already plug in certain things. I know that dx dt is 3, and I know that dy dt is 4. So I don't need to wait any longer. I can just put those in. Here's what I have. I have x, there's 3, y is 4, y prime is 4, and what I don't know is z prime. Now, after 1 hour, what is z? So this is one of the things. Notice I don't know z either. I've got to figure that out. After 1 hour, what is z? Well, what is x after 1 hour? It's going to be 3. So in this case, we got 3 times 3. What is y? Well, it's 4. Okay. So this is a simple one, right? Now, what would be z? Yeah, because this is a 3, 4, 5 triangle. We're just really being simple here, making it very straightforward. So now I have a simple algebra equation, right? I have 9 plus 16. Okay. So here is 9 plus 16 equals 5z prime. That's going to be 25 divided by 5. So this is 5 equals z prime, right? Okay. Okay, do y'all see that? Now, this is a simple one, and I just wanted to start off with something very simple so that it's very intuitive. Now, you can spice these up a little bit. For example, I could have said, Okay, one person is walking east at 3 miles an hour, the other person is walking north at 7 miles an hour. How fast is the distance between them after they've been traveling for 3 hours? Okay, so let's spice it up a little bit. Let's suppose the same problem. Let's change it. I have dx dt is equal to 3. dy dt is equal to 7. And I'll just leave off the units. Okay, now our problem is just a little more complicated because and we want to find dz dt after, let's say, 3 hours. Okay, let's suppose that's what we want to find. The same picture applies, only the numbers are a little bit different. But here's what we've got. We've got x squared plus y squared equals z squared. Same relationship. We go through, we have 2x x prime plus 2y y prime equals 2z z prime. Okay. And I will just divide out the 2's as usual. Okay, there's what we have. Now, remember, we've been walking for 3 hours. Okay? So the distance, the horizontal distance down here is 3 times 3, right? So this is going to be 9 times 3 right there, right? Now, the vertical distance on this triangle is 3 times 7. So that's 21. And this is 7. Does everybody see that? Okay, now we got to find z, right? Well, how would you find z? What do you got? Here you got 3, 21. So is that right? 9, 21, right? 9, 21? I got it right now, right? Okay. Now, so this up here is going to be the square root of 21 squared plus 9 squared, right? And that is going to be z. That right there goes in right there for z. And then it's just simple solving for z prime, right? Now, notice every time what we have to do is we have to find out how our variables are related. Once we find out how our variables are related, then we differentiate to find how the rates of change are related. So let's suppose this, let's just look at this situation. Let's suppose that you're making some flapjacks, okay? And you pour the batter out on the griddle, and we're just looking at the top, the surface area. And let's suppose that it's making a perfect circle. In other words, it's expanding out in a perfect circle. It's probably a bad choice of an example. That would never happen. Maybe I should have chose drop a pebble into the water and the wave goes out in a circle. But let's just stick with the flapjacks because it's near lunchtime. Now, let's suppose this is true. Let's suppose that in this situation that the radius of those flapjacks is changing at, let's say 3 centimeters per second. Okay, let's suppose that's the case. Now, and let's suppose that, let's just give it a value. Let's say when t equals 2. After you've been pouring this flapjack batter for 2 seconds, the radius is changing at 3 centimeters per second. Now, we want to find how fast is the area changing. That's what we want to find out. So first of all, we want to figure, in other words, we want to find dA dt. So the first thing we think about is, well, I wish I had a formula for a circle that relates area and radius, okay? And we do, right? Area equals pi r squared. Okay, so now we can put on our differentiation boots and say, okay, dA dt is equal to 2 pi r dr dt. I just got away from the r prime there. Okay. Now, let me make one change here. Just for simplicity's sake, let me say, instead of when t equals 2, let me say the radius equals 2 centimeters. Okay, let's do that. Let's do the radius equals 2 centimeters. So the radius is changing at 3 centimeters per second when the radius is 2 centimeters. Okay. Now, if I do that, notice now I have everything that I need because I can plug in now. So I can say, okay, dA dt when the radius is equal to 2 is equal to 2 pi r, right? Just put in a 2 there, dr dt, and dr dt is 3. Now I left off the units here, just, but does everybody see that? Now you notice if we did put in the units, you would have 2 centimeters here, 3 centimeters per second here, and that would end up being squared centimeters, right? Centimeters, right? So the units would work out, but we're just trying to get this part down. Well, it looks like that's it, doesn't it? What would that be, 12 pi squared centimeters per second? Okay. Looks like that's how fast the area is changing. Okay. Now, you notice here, so what you're always looking for, you're looking for a way to relate the variables. If you were dealing with so you're dealing with a circle here, pi r squared. If you were dealing with a sphere, then you would have, the volume of a sphere is 4/3 pi r cubed. So that's a good one to keep in your knowledge pi, right? The circumference of a circle is 2 pi r. The surface area for a sphere is 4 pi r squared. Okay. It's interesting, it's the derivative of that. Okay. Any questions about that?